You know, somewhere, right this second, a machine is making a decision about you. But how do we know if that decision is fair or even right? Well, today, we're going to pull back the curtain and see how we can get machines to explain themselves. And believe it or not, it all starts with one beautifully simple and really powerful idea: a single straight line.
It sounds a little too simple, doesn't it? I mean, our world is messy, it's complicated. How could one little line possibly tell us anything that actually matters? Well, that's the mystery we're going to unravel today. We're on a quest to find the answers hidden in the data patterns that are all around us.
Okay, let's have some fun with this. Put on your scientist hat for a second. You've gathered all your data, you've got hours studied and exam scores for a bunch of students. You plot them on a chart, and each student, they just become a single dot. What you're looking at is this cloud of points, kind of drifting up and to the right. There's a story in there, a secret just waiting to be discovered.
Now, to crack this code, you need the right tool, and that tool is called linear regression. It's this amazing method that doesn't just draw any old line through those dots. Nope, it finds the one, single, mathematically perfect line that tells the truest story of the relationship hidden in that data.
Okay, so this line gets described by an equation. And I promise this is not going to be some scary math class flashback. We're going to build it together piece by piece. First up is y. Pretty simple. This is our target. It's the answer we're trying to find. For our students, y is their exam score. It's the thing we're trying to predict. All right, next we add this little thing called B0, or the intercept. The easiest way to think about this is it's the model's baseline guess. It's the starting point. So in our case, it's the score our model would predict for a student who studied for exactly 0 hours. It's what we assume before we know anything else. And now we get to the really cool part. We start adding our features, the x's. These are our clues, like the number of hours someone studied. And each clue gets its own multiplier, a b coefficient. This right here is where the magic happens. These coefficients are what the model learns, and they tell us exactly how much each clue really matters. And finally, we add this little Greek letter, epsilon or epsilon. This is the error term. You can think of it as the model's way of being honest. It's admitting that, hey, no prediction is ever going to be absolutely perfect. There's always going to be a little gap between the prediction and reality. Epsilon is all that stuff our model just can't explain.
So how in the world does it find that one perfect line? It uses this really elegant process called the method of least squares. It's pretty intuitive. First, it just takes a guess. It draws a line. Then for every single dot, it measures the distance to that line. That distance is the error. Step 3, it squares all those errors. Now, why does it do that? To make the big mistakes count for way more than the small ones. And finally, it just keeps wiggling that line around until the total sum of all those squared errors is as tiny as it can possibly get. And bam, that's your best line.
Okay, so student exams, that was a good warm-up. But let's take this to the next level with a bigger mystery. Let's say we want to predict how many bikes will get rented in a city on any given day. Our clues, our features are going to be temperature, humidity, and the season. Let's see what the line tells us this time.
So the model spits out this table, and it basically reads like a story. That intercept, 3200, that's our starting point, our best guess for a cold, non-humid winter day. Then you see temperature has a coefficient of plus 120. That means for every single unit the temperature goes up, we can expect about 120 more rentals. But look at humidity, it's minus 50. So stickier air means about 50 fewer rentals. And then get this, just the fact that it's spring, that adds a massive 862 rentals all on its own, compared to winter.
Now, you might be wondering how we can be so specific about these numbers. The secret sauce is a principle called ceteris paribus. It's just a fancy Latin way of saying all other things being equal. So when we say temperature adds 120 rentals, we mean if humidity and the season don't change at all. It lets us cleanly isolate the effect of just one thing at a time, which is what makes these explanations so powerful and so fair.
But hang on a second. If you look back at that table, temperature is a number, humidity is a number. But spring? That's a word, right? It's a concept. How on earth can a math equation understand what spring is? It seems kind of impossible. But the solution is actually really clever.
We use this neat little trick called dummy variables. All we do is create new columns in our data for these yes or no questions. Is it spring? If yes, it gets a 1. If no, a 0. Is it summer? Yes, a 1. No, a 0. We do that for autumn, too. And winter just becomes our baseline, where everything is 0.
And just like that, we've translated the messy, real world into simple ones and zeros that math can totally understand.
Now, this is a really powerful tool, but it doesn't just work on any old data. As a good scientist, or really any student trying this out, you have to follow a code of conduct. You can think of these as the 5 commandments of linear regression. And they're not just annoying rules, they're critical checks to make sure the story your model is telling you is actually true.
Let's look at the absolute most important one, linearity. Your model can only draw a straight line. That's its only move. So the real relationship in your data has to look something like a straight line, like the chart on the left. If your data clearly has a curve in it, like the one on the right, and you try to force a straight line through it, well, you're going to get a completely wrong and misleading story. This is exactly why you always have to plot your data first.
And this really brings us to the whole point of using this simple model. It might not always be the most accurate model out there, but its real power, its superpower, is something else entirely. As our source material puts it so perfectly, it speaks in a language that humans can read. We can just look at those coefficients and we get it. We understand why it's making the prediction it's making.
So this simple, readable line we've been talking about, it's the bedrock, the absolute foundation of what we now call explainable AI. It's our key to unlocking the black box of a machine's decision-making. It gives us the power to look inside, to question the logic, to check for fairness, and ultimately to hold these incredibly powerful algorithms accountable to us, to people.
So, the story that started with a single line really ends with a pretty deep question for all of us. As AI gets more and more involved in our lives, deciding everything from loan approvals to medical diagnoses, we now know we have the tools to ask why. We can demand an explanation. The only question left is, what should we demand our AI explains next?